Right. Hey, everyone. My name is Amijai Saragovi. You can call me Ami or whatever you find it you're 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 comfortable with. So today I'm going to talk about the vision we're trying to build in Lund, me and a few other people. We're doing this in kind of under the umbrella of Lund and Vinova that gave us the money to do that, and basically trying to build a roadmap from some of the research I did during my postdoc in the Baker Lab to try to bring it into reality of something that will be maybe useful for everyone. If you want to learn more about it, you can go to InBio, so like in biology, inbio.design, and you can find more information about events that are happening. For example, there's going to be a bootcamp in April and a hackathon as well, where people will have a chance to have a hands-on experience in protein design. Okay, so today I'm going to tell you a little bit about what you can do with protein design and specifically how you can use protein design to build potentially electronics, and why do we need it. Um, the talk is quite, I would say, intermediate. If you want to learn a bit more after the lecture about, or after the talk about protein design, there are wonderful talks online in the recent Nobel Prize lecture. So you have David's talk and John Jumper's talk, and they're quite good in explaining in more detail about what you can do in general in protein design. But today I'm going to tell you more about what you can do in the field of electronics with protein design. Right. So let's start with why. Why do we need to build things with proteins? So, you know, all the tech we have here and a lot of the tech that you have yourself is going in 1 year, 2 years, 3 years to be dumped. And these are, maybe we don't see it, but these are hard to recycle. My mobile phone probably contains the entire periodic table. It's really some toxic stuff, and this is going to be buried. Sometimes it's treated well. I think in Sweden it's not bad, but mostly it will be polluting the ground, polluting the water. So we're basically building up the next plastic problem. Just instead of having like plastic as an inert thing, we're taking super toxic stuff and we're generating a lot of it. How big is the problem? Okay, so 62 billion kilogram big of e-waste so were tracked in 2022. Only 13.8 billion of these were kind of documented as collected and recycled in kind of okay fashion. And this is a UN definition of okay fashion, not Sweden definition of okay fashion. So that's not necessarily very okay. A lot of this, as you can see, is just remained as dump or just being thrown in other ways. So that's kind of a big problem. Um, yeah, this is a bit more stats around it, so you can see, the distribution. You can basically circle the world a few times with the amount of trash that we generate per year. I think it's 7.8 kilo per person on average. So that's much e-waste we're generating. Most of it is metals, some of it is plastic, and then some of it is other materials. So really complex kind of thing to get rid of. Um, yeah, and this is not getting better. So we have a problem. We are making all this stuff. This is not going away because we need the computers for work and for pleasure and for everything now, especially with now this revolution in automation and AI. So this is not going away. This is the trend will get worse. So I think it's predicted 120 billion tons kilograms in 2030. So this is going to get worse. Another problem we have with e-waste is that if you recycle e-waste in the normal way, you end up with a bit like a few. So if you take a lot of mobile phones and you recycle all the materials, you're not going to end up with so much material in comparison to what you will get from mining the materials directly. It just a lot of energy to get something that is not valuable is not going to incentivize people to do the job normally. That's a problem. So we need to find a way to make some things that are very valuable from this waste. If we would just recycle it, it's a problem. So we need to kind of generate waste into gold rather than waste into the basic material that it's made of. Okay, so what can we do about it? Right. So nature tend to be a good source of solutions for a lot of things. So maybe we can learn a bit from nature how to deal with inorganic materials. And I'm going to give a few examples, and I will try to be as detailed. So there are what you see in one is basically a zoom in on a part of a sponge. So sponge is kind of a creature that looks like an organism that look like a sponge. Mostly it's just made of cells, but there are a family of sponges that are made of silica, so they are made of glass. And actually they're making these tiny fibers here that are known to be better than our best optical fibers that we use for running internet. And these are scaffolded by proteins, so you can see in the top assembly of proteins. And then this assembly knows to take the silica through enzymatic process and kind of organize the silica into very defined structures. And look at the resolution here. This is 20 nanometers. This is kind of the resolution you will find in a computer chip, right? Another example is the magnetotactic bacteria that literally builds these nanocomposites. So they organize iron into magnetite, which is a form of magnetic iron oxide, and then they organize it inside the cell to find the north. And this is how these bacteria are navigating. These magnets are better than what we can do in a lab. So they're making things that better than what the best lab we have can make in scale. And look at the size of it. This is kind of, each one of them is about 48 nanometers, which will go a lot of times into one of your hair, which is 100 micron, just to put things in scale. The entire bacteria will go many, many times into your hair. So this is tiny. Finally, we see an organic crystal, actually, here in 3. This crystal is growing in fish to reflect specific wavelengths of light. It's called guanine, beta guanine crystals. And again, you have a protein that templates an organic crystal that is tiny into something functional. And there are even creatures that see that can build eyes just from this crystal. There is a reason for this, like physics, but evolution took the path of building eyes from crystals using this. So they can organize it into very functional structures. Right. So now I'm going to talk about introduction to protein design, because I told you how nature is solving it, but we cannot just take parts of nature and kind of put them together into something that will work. We need different materials, we need different shapes. So we want to control exactly what nature is doing. And I just showed you that nature can do very specific shapes. So if we maybe can do another type of shape and start to create semiconductors instead of glass, or our bones, for example, hydroxyapatite, then maybe we could do something useful, right? So first, let's talk a bit about protein, and then move to protein design, because some of you might not be familiar with proteins and proteins design. How many of you have thought about protein with outside the realm of food before? Okay. Okay, so for some of you, proteins were food until today. Most of you thought about them in a slightly more complex way. So, okay, so this is, I stole some slide from David. So that's from the lecture. You can see all the examples from there. But basically, there's a nanomachine that run our cells, and basically everything living around us. It's just a lot of these nanomachines that scaffold, catalyze, and kind of structure the way the cells work, right? So you have all these nanomachines. And basically the way they work is that we have a gene in our body that encodes this polymer, this chain of amino acids that forms a protein. And then because these building blocks have different chemical property, they will fold into a structure. So two problems fascinated biologists for many, many years. And the first problem is the protein structure prediction problem. And this problem says something like this. If I have a sequence of amino acids, so this is a sequence over here that is translated from DNA via RNA to a protein, what form, what 3D structure this sequence will make? And this was a huge problem, and for years, people were trying to solve this problem, and this problem was basically solved by DeepMind, that they developed a model called AlphaFold 2. To be fair, we published the same day Rosetta Fold that did the same, but we were inspired by them. When I say we, it's a Baker Lab. But they won. So Google and John Jumper and their team won the Nobel Prize for the structure prediction. So basically, the idea here is that we now can take a model the same way you take ChatGPT. We can give it a sequence of a protein, and it gives us a structure. Okay, so we have an oracle. We give it a sequence. It tells us how this protein will look in 3D. The second problem, which is a protein design problem. So this is kind of the reverse problem. So imagine you have the 3D structures that you created. You want to know which sequence will fold into the structure. It could be more than one sequence that will fold into the structure, but you want at least one that will fold into the structure. This is also a very hard problem, and for this, this is now could be done, for example, with a model called MPNN, and then you can get a sequence that will fold exactly to your target model. Again, a deep learning model. So you also need to create this shape. For this, we have another model, but I will touch it in a second. So this is kind of how the process works. Here, so you start with a model called RF diffusion, which basically uses the same mechanism that people use deep learning to diffuse a picture. I will not go into the many details, but basically you're training the model to based on, you take a picture and you introduce noise, random noise into the pictures in many steps, and then you start with a complete picture, right? And then you have a lot of noise, so a lot of noise. And then if you have all the step between your complete picture and a lot of noise, you can now train the model to generate new pictures. So that's kind of the principle of diffusion. You can do the same thing in 3D with atoms and proteins. So basically, the model learned to take this chaotic noise and creates a protein. The nice thing is that you can then restrict it the same way you're restricting ChatGPT by giving it a very specific prompt. So you can tell it, don't make it bigger than this. Connect it to this, and then, or make it to bind this piece over here. So you can create a shape based on kind of very specific restriction of size or binding. Then you have a shape, and like I said, you need another model to get a sequence. So the first model gives us a shape. Second model gives us a sequence. So now you have a sequence, and you want to test this sequence. So then you put it to a third model, AlphaFold. Used to be AlphaFold 2, now it's AlphaFold 3, which you could, by the way, can find online. It's for free. You can just log in, take any protein sequence, throw it in, and you will get a structure, right? So then, through these different models, you can start from literally just a vague idea of what you want. You will get a protein structure. You get a sequence. You can test the sequence, and then based on the score and the confidence, just orders the DNA and makes a protein. So kind of this is how we work. We first sit down, we create a lot of designs, we filter through all kind of parameters. For example, we can say, okay, we want proteins that are very negative, that tend to express well, just very technical issue. So we can filter for the ones with the right properties other than what we force the model to do. And then we can just literally print them. We get them by mail. We mix them with bacteria, sometimes with yeast as well. The bacteria grow, and we get a lot of protein. And you can do this now for tens of thousands of protein in 1 week. So we can get to a place where we work on a model filter, and from the points that we have, I don't know, 1,000 designs on the computer, get 1,000 different real protein in the real world in a week. So this is how fast this process is. And then obviously you learn from it, so you can continue. Okay, so now you learned a bit about protein design. If you want to learn more, I suggest again, go to the Nobel lecture, hear more about it. But I want to tell you a bit how we can use it maybe to make our world better in terms of e-waste and alternative way to make electronics. So let's talk a bit about the vision. So our vision, the way we see it, is that you take a lot of e-waste, you put it in a liquid in water, but that could be a very acidic liquid. You kind of dissolve the periodic table out of them. And then bacteria are very good in taking metal. Actually, it's very important for them to take iron, but they will also take other metals. So they are taking the metals, and you can take different bacteria that are resistant to the toxicity of some of these metals. So then inside these bacteria, you have the designs, and then maybe these designs can guide exactly the shape we need, and then we can create something like a nanowire array that is used as really good solar cells or sensors for satellites, for example. But you can also think about other applications. Right, so let's talk a bit about where we are, which is kind of what I did during my postdoc. And this is kind of where things can get a little bit complex. But if you don't understand something, first you can ask me at the end. And then also, it's not that important that you understand every slide, right? So let's go through it. So first of all, how do you even approach this problem? Okay, so let's say I can do any shape I want, but what shape will cause a semiconductor to form? Right, that's what chemistry is out there. And the answer is, at least 4 years ago, we didn't know. So we had no idea. Natural proteins that are doing this are not doing it to this materials. These are semiconductor materials nature is not using, so we didn't have any evidence. And also, most of the proteins that are doing this are not properly folded with AlphaFold, so we didn't really know what answer is. We do have proteins that are well studied, that are basically preventing or interacting with ice. So we could learn some principle from that. Anyway, just to get you a bit around the physics of how this is work, and don't worry, it's kind of very simple. So let's start with the top part, 1. So normally when you have water and you have salt in the water, by salt I just mean ions, if you keep on adding ions, you will get to a situation where the ions will want to form a crystal. You know that because if you forget glass with salt or sugar and on your table and the water will evaporate, you will come and you will see lots of white things. And these white things are crystals that form because of, let's say, the NaCl that you added to, which is salt, which table salt, which you added to your water. But sometimes you're in a regime or in a concentration that's supposed to form a crystal, but you don't get a crystal. Maybe some of you seen online a YouTube video of water that you put in the freezer, and from some reason the water don't freeze, but then you kind of touch it and it's freezing in one go. That's kind of the same phenomena that I'm talking about here. So you're in a solution that wants to go and become crystal, but it's kind of stuck. It's creating a very small crystal initially, and because this crystal has a lot of surface in respect to volume, it's mostly unstable. So then it's going back to ions, and then it's kind of stuck in this loop. And if you give it enough time, like 100 years, or maybe a month, it will come out of this loop and will grow, but it will not happen immediately. What happened with what I call the template is that, or let's say for the sake of it, a protein, is that it binds one of the surfaces of this uh, tiny crystal, and then it's kind of lower the need for it to dissolve, so it's allowing it to grow, and then you get a big crystal. And then this will happen almost immediately, or you will cut the time by a lot. So this is kind of how biology is doing it for ice, for example, ice nucleation, or for our bones and stuff like this. This is kind of the physics that our body is using to grow crystals. Uh, how exactly they bind those little crystal, we didn't know. We thought about three things. One is that just a charge matching. So the crystal will have, I don't know, a surface with a lot of positive charge, and the protein will have negative charge, and they are organized the same, and there's a good match, negative and positive. There are problems with this assumption, but we had to go with this. Another thing is the metal coordination. So proteins are able to what is called to coordinate. They kind of bind the ions. And if you organize the ions in exactly the same order of the crystal, maybe this matching will help to bind. And finally, we know that on the surface of solids inside water, the water are organized. They're very similar to ice. So maybe all the protein need to do is to organize the water around the surface of the protein, and they will bind. So this is kind of how we started everything. Yeah, so then you really use the power of protein design. You start by creating a lot of scaffolds, right? Scaffolds are proteins that have a certain defined sequence that you cannot change. So they will have like a fixed sequence that you cannot change. Mostly between, so you see the yellow dots is places that you can change, and inside the proteins there will be positions in the chain of building blocks that you cannot change. These positions force the protein into the specific shapes, and then you can diversify the chemistry. So then you have a really nice tool. You can design a lot of these scaffolds and just randomly change the chemistry to interact. So we build a lot of these scaffold with different kind of shapes, from these very flat beta sheet-like solenoids, alpha helixes, and kind of created this base library. Then we kind of thought about different surface chemistry. So then we can just randomly add different amino acids to them on the surface based on the assumption I told you before, right? And you can do it in a periodic way. So basically, every position will repeat in every repeat of the protein, right? So it's kind of very repetitive. Or you can do it in a chaotic way, right? Where basically nothing is repeating exactly the same way. And then we needed some. By the way, we made something like 35,000 proteins this way. Okay, so it wasn't a small number. A lot of DNA was ordered. So then we took the base scaffold, we diversified the chemistry of them. So then we got like a lot of sequences. We ordered everything. We expressed them on yeast in a way that they will cover the surface, and then we mixed them with the nanoparticles of the material we were looking at, which was then zinc oxide, which is a semiconductor with relatively wide band gap, if anyone know what it is. Anyway, it's useful for some things. And then hematite, that is normally used for breaking water and producing hydrogen in an efficient way. So it's a photocatalyst. So each one, we kind of mix it and we enriched. We're based on their kind of scattering, we were able to enrich. You don't really need to understand exactly how it works, but we're just taking those that are binding better, the nanoparticles. Okay, so we found a few, right? So these are the ones that we found for hematite, and these are the ones that we found for zinc oxide. And you can see they are slightly different. This one, and this one have amino acid called histidine, which is not surprising because this is amino acid that is used to bind metal by nature. So not that surprising. This one was kind of surprising because it has almost no residues with charge and almost no coordinating residues or no coordinating residues. So we were like, huh. But it did look like proteins that bind ice. So maybe this one is organizing water. Anyway, okay, we found something. We display proteins that are sticky to nanoparticles. Maybe we got it wrong. Now we really need to show that they kind of able to template to speed up the formation and the localization of the semiconductor, right? That's kind of the next job, right? So this is a bit gruffy. Don't know how much you're familiar with this kind of things, but the main thing is to understand kind of the take-home message. So first, let's start with this one, top left. Basically, we're talking about time, right? Because like I said, if you will wait enough time, things will happen by themselves. So we want to find things that speed up things. So what we did here is that we did a little trick because it's very hard to identify the hematite. So this was for hematite, which is iron oxide, by the way. We created conditions that will create magnetite. Now, magnetite is magnetic, so it's really easy to see when we basically took a plate and we put a magnet underneath the plate. So then when magnetite formed, it was really easy. So like everything became black and was sticking to the bottom of the plate. And if something else is forming, then it's kind of interesting. If everything looks red and not black, and it's not going to the bottom of the floor of the well, then it's starting to be interesting. So you see, this is kind of empty one. Lysozyme is another protein, but Him9 is slightly higher. But Him7 really looks like this is kind of the redness of the well. First of all, it's not becoming black, and then it's even increasing the redness. So that was kind of interesting news. What you see here on the right is a technique called Raman. Again, you don't need to understand the details, but think about it as a way to fingerprint a material, right? So every material has a fingerprint, and you want to find the fingerprint of your material. So here in the bottom, we have the reference. Like I said, the default of this reaction was to form magnetite, right? We selected proteins that were apparently supposed to template hematite, right? So here in the bottom we have the reference. So reference for magnetite, reference for hematite. This is what happens when you put lysozyme or just a buffer. So buffer, just you added nothing basically. You see pattern, a fingerprint that is very similar to magnetite, as expected, because everything went down and was magnetic. So wow, what a surprise. But when we added our protein, we get a completely different fingerprint. So the protein caused the material to become to get a fingerprint of hematite. So that was exciting, right? Zinc oxide is more easy. It's just it's become photoilluminescent. So it has a band gap that can basically take light, convert it to another wavelength, which is really easy to track. So as you can see, this is kind of our positive control, which means we use nanoparticles as templates because they are templates. They're exactly the form of the thing. So you can see how it's starting low and growing. This is our proteins, so you can see that they're not as good as the nanoparticles, but they go up after about 60 minutes. So somehow when we add these proteins, we get this fluorescence out of the solution, but when we add just control, we get nothing. And again, this is another method called XRD, so we can show that they're making the right material. Okay, so if you didn't understand the entire technical stuff and you want to ask a question afterwards, I'm happy to tell. But basically, we found that if we add our proteins, we're generating the materials that they were selected for. So that was nice. We're at the right direction. Another funny thing is that we found that at least Him7, which is one of the proteins that was selected for hematite, is blocking the formation of rust on iron. So we add just we take a clean iron surface, we add something water with salt and some of the protein, and we get rust. So we do the same with just water and salt without any protein, we get rust. But we add our protein and suddenly we block most of the rust. So this was kind of, okay, interesting what's going on there. But it remains to be seen what is going on there, but obviously the protein knows to interact with iron. So that's interesting. Right, so now we wanted to start understanding more and move further with protein design uh, towards making interesting stuff. So this was a very potent zinc oxide against a semiconductor binder, and it was also a template, but we noticed that it's forming fibers. You can see here, this is 200 nanometers. Uh, yeah, so this will go quite a lot into your hair. I'm not going, but these are very tiny, basically. Um, so this is not so good because basically it's forming these fibers, and the protein, they think the protein cannot really interact with all the well. So we're thinking maybe the performance are not so good because they're making these fibers. So then we can take just the motif, right? So we can identify the motif, just take basically the parts of the protein that we think that is making the activity. And then we can create new proteins just by giving it as a prompt to a diffusion model and say, can you finish this for us, please? Because this will not work by itself. So then we design new ones that are built not to form these fibers and tested them. And this is kind of a summary. So this is kind of how fast these proteins are creating photoluminescence in the well. And this was, at least this one, which we called ZAB3, was super potent and was actually faster than our positive control. So this was quite amazing. And look at the improvement. So this was the original one. It took something like 50 minutes to start picking up, and the improved one was less than 20 minutes. So really big improvement just by redesigning. So again, here we're taking the active part from the protein. We use it as a prompt to our model, generating new designs. Right, so now we can start going into shapes, things that are more interesting. So what you see here is two types of what we call oligomers. So proteins, up until now, we looked at a protein, one protein. But you can design protein to form shapes by coming together according to geometry. So instead of now diffusing just one protein, you're diffusing a protein with symmetric constraints. So for example, you can give it what we call cyclic C3. So it's kind of a cyclic oligomer. So you just need to rotate your protein around the center, and you have three components, and then you form this triangle where the motif is oriented toward the center. And you can see here the experimental data. So this is kind of TM and reconstruction showing the proteins that we design on the computer in real life. So they are forming. We also got a crystal structure. You don't see it here, but because you're a bit far, but there is gray and blue, and they're basically spot on. So we made this triangle, we made this C6, and then we tested whether they can nucleate. And you can also make like 3D structures. So you can make these protein cages that basically you take this triangle, you create more interfaces according to symmetry, and you can create an octahedron. And in a similar way, you can create like a tube that have internal volume with the interface. So now we're starting to move toward making small things with defined shapes, which is kind of what we want for making electronics. Right, and this is kind of where we are. So if we put the protein with the ingredients, you see black things starting to grow on the proteins. And we kind of got a few different results. Some of the protein remain empty. This is probably to do with my silly starting conditions of the optimization of the reaction. Some of them were filled, so we got a filled octahedron with a semiconductor. Some of them kind of escaped the cage, so kind of grew out of the cage, probably because we thought it would be cool to put it here, and we should probably have put it inside the interface to force it to cage, but it is what it is. And some of them form dimer, where the zinc from two cages kind of created a shape in the middle. So we're not exactly controlling the material yet, but we're getting close. Um, you can see here that when we reconstruct everything in 3D, so what you do, you collect a lot of photos from a lot of angles, and then you can reconstruct everything in 3D. We get exactly the interface that was planned. We get this bulb, and this is kind of the center of of where the analysis find density of zinc oxide. So you can see that this is kind of empty, but this is full. That's nice. This is kind of where we planned, and this is further analysis showing how the atoms are interacting with the interface. So we got it right. It's just that it's only constrained in 2D, so it can escape randomly to 3D through the Z axis in each one of the triangles in the octahedron, and then forms this mixed output. Okay, so kind of this is where we are now. How do we get to something that will be useful for society? So first of all, we need to learn how to do things that are useful. So we start with doing small defined shapes. That's kind of my next 5 years of research. And then we can, for example, see the quality of the crystals. We can check the conductivity and see whether we can use them as materials in the same way like output from a clean room will be used for electronics. Then we can start working on organizing them into D. This is the way you should think about it, is the same way as sometimes on cell membranes you have proteins that are organized on the cell membrane. You can use this property of proteins to organize your proteins on a 2D first, and then add the semiconductor. So basically you're first organizing some sort of a chessboard based on your small, let's say, cubes. And then after you organize it, and maybe you organize it in a way that some will be zinc oxide, some will be silica. So then you create a very unique pattern. You can create this 2D materials that are super defined in the nanometer level. Finally, you can organize it in 3D, which is beyond or almost beyond what we can do today in the clean room. So, it will take some time to get from top to bottom, but this is kind of the direction shape-wise. You can also think about it in terms of the material we're using. So you can start with one material in a very simple way. You can move with creating like a junction between two materials. So now let's say you have two boxes. One of them is made to create one semiconductor. The other one is made to make another semiconductor, and they create a junction between them. So now you have like something very tiny that creates a junction between two different materials. And then you can do something very complex that kind of looks like a diode or a quantum dot that you can connect to a circuit already. You can also dope. So doping, for those of you who don't know, not that I understand it very clearly because I'm not a physicist, is adding a very tiny bit of another metal to your semiconductor. And just by doing this, you completely change the properties of the semiconductor. So you can do N doping and P doping and so on, and then create diode, which are in all your computers and mobile phones. That's kind of the basis of everything we do now with computers. So if we could do that and we could do 3D, we're getting close to making a GPU in bacteria. And then kind of what are the applications? So if we can create this, for example, these nanowires, you can, and the conducting nanowires, for example, you can detect, these things conduct light very well. So you can detect, for example, almost every molecule and very, very accurately inside a drop of blood, because the light will just run through the nanowire. You can make other detectors. You can make solar cells with this, because again, they know to capture light very well. So this will be great. So obviously I said 2D and 3D, so you can think about other electronics. And then if you're more interested in kind of biology, medicine, perhaps, then we can learn from some other organisms. So what you see here is a cable bacteria. So it's bacteria, by the way, the researchers that found it was in Denmark. So these bacteria are literally building an electric cable inside them, and they conduct electricity along centimeter long cables, living cables. So so it's a chain of bacteria, and they kind of run it. And you can see the shape here, but or just read about cable bacteria on Google or whatever. So we can think about starting creating in, let's say, immune cells, RFIDs on literally control cells with a joystick, or talking to cells the same way we're talking to things. So all the powers that we have in mobile phone can now maybe start potentially be used to enhance, to make, let's call it, biohybrids or smart cells. So this is kind of another application which I don't focus on right now, but this could definitely be another application of this technology.